It is April 10th. After a historic 10-day journey around the moon, 4 astronauts are in freefall, heading straight for Earth. Look at this orbital map. It traces the capsule's final trajectory, tracking a spacecraft moving at nearly 25,000 miles per hour toward a highly specific target zone off the coast of San Diego, aiming for exactly 8:07 p.m. Eastern Time. Down in Houston, flight controllers are monitoring every telemetry ping. They are guiding home a crew that has traveled farther into deep space than any humans in history. Pushing a capsule to the far side of the moon requires immense propulsive power, but scrubbing all that speed and surviving the violent return trip is the ultimate test of this mission's engineering. This diagram illustrates the razor-thin margin for atmospheric entry. If the capsule approaches at an angle that is too shallow, it will bounce off the upper atmosphere like a stone across a pond, sending the crew drifting into deep space with no way back. Conversely, if the angle is too steep, friction increases exponentially. The spacecraft would instantly exceed its thermal limits and burn up. Even if the geometry is perfect, the crew faces an uncontrollable environmental threat. A cold front is currently hovering right over the recovery zone in the Pacific. This layout details the strict limits set by NASA and the Navy. For a safe recovery, there can be 0 rain within 35 miles. Winds must stay under 29 miles per hour, and wave heights cannot exceed 6 feet. A fraction of a degree in approach angle, or a localized rain shower in the Pacific, puts the entire recovery operation in immediate jeopardy. To hit that precise entry window, the capsule made a crucial adjustment. At 10:53 p.m., the European service module fired its auxiliary thrusters. That burn lasted just 9 seconds. It changed the spacecraft's velocity by only 5.3 feet per second. In orbital mechanics, that tiny nudge is the equivalent of a sniper shot to align the capsule with the California coast. Inside the spacecraft, the crew executed their own precise maneuvers. They spent their final hours meticulously securing loose gear against the capsule's dense interior framing. During re-entry, the astronauts will experience up to 3.9 Gs of deceleration. Under those loads, a floating camera or unsecured sample container instantly becomes a high-speed, deadly projectile. Coming home requires absolute discipline inside the cabin, perfectly synced with the orbital mechanics happening outside. With everything strapped down, the crew module detaches from the service module. It then crosses the entry interface, the boundary 400,000 feet above the Earth. Hitting the atmosphere at 25,000 miles per hour violently compresses the air in front of the heat shield. This compression generates a superheated plasma envelope around the capsule, pushing temperatures near 5,000 degrees Fahrenheit. This abstract diagram shows what happens next. The dense plasma field physically absorbs and deflects the spacecraft's telemetry radio waves, completely cutting off communication with Earth. The hardware enduring this heat has a complex history. During the uncrewed Artemis I flight, engineers noted unexpected material loss and charring along the ablative heat shield located on the capsule's curved base. To compensate, mission planners adjusted Artemis II to fly a steeper trajectory. This reduces the total time the capsule spends inside the intense heat, but pushes the shield's structural integrity to its upper limits. For 6 agonizing minutes, Mission Control sits in total silence. They are entirely blind, trusting the physics and engineering to protect the crew inside the fireball. When the communications finally click back on, the thermal survival phase is over, and the aerodynamic sequence begins. This deployment schematic reveals a highly choreographed sequence, firing 11 parachutes in distinct stages, moving from drogue chutes to pilot chutes, and finally to the 3 massive main canopies. This system applies immense braking power to the 4-ton capsule. In a matter of minutes, the spacecraft decelerates from 130 miles per hour down to a gentle 17 miles per hour. A precisely timed sequence of deploying nylon is all that separates a lethal ballistic plunge into a survivable ocean touchdown. At exactly 8:07 p.m., the spacecraft hits the water. In that instant, the mission transitions out of NASA's jurisdiction in the sky and into the hands of the U.S. Navy on the ocean. The USS John P. Murtha, a massive amphibious transport dock ship, has already steamed into the recovery zone to coordinate the retrieval. Elite Navy divers immediately deploy in small boats. Their objective is to reach the bobbing capsule, verify it is safe, and attach an inflatable front porch for the astronauts to exit onto. This water recovery is a highly coordinated military operation, executed with the same precision as the spaceflight itself, to secure the crew's survival. Once on that raft, helicopters have a strict 2-hour window to hoist the astronauts from the water and fly them to the Merthyrs Medical Bay. After 10 days in microgravity, the fluids in the astronauts' bodies have shifted upward. Their cardiovascular systems need immediate medical evaluation to safely handle the sudden, crushing return of Earth's gravity. The safe extraction of these 4 astronauts provides the final, vital data point. It proves the Orion capsule's life support and thermal protection systems can handle the realities of deep space travel. This successful splashdown brings the crew safely back to Earth. And in doing so, it clears the path for the next mission, to put human boots back on the lunar surface.